So the purpose of this talk is to go through the causal topology of neutral four manifolds with null boundary, a paper posted on the archive by myself and Nikos Georgiou recently. The general topic is one of neutral geometry. So let me start there. Now we're going to start with the simplest possible case. So if you just take the flat case, so take R4 and take an indefinite metric whose eigenvalues are 1, 1, minus 1, and minus 1. So if you like, the signature is 2, 2. And let's call that R2, 2 for short. Now, this signature metric is a little bit unusual and has a number of different features which are worth focusing on at this point. The first one is the null cone. So the null cone is essentially the set of all null vectors associated with this metric. So the null cone, let's call it K, is the set of all vectors x in R4, or in fact R2, 2, if we're going to use that notation, such that their length is 0. So the set of all null vectors. Such a cone, in fact, it's actually a cone over a torus. If we were to draw it, what we would see is a torus like that, and then we would cone it over the origin. And so what's interesting about this, as distinct from the Lorentz case, is that the cross sections here, these tori, of course, are non-simply connected. So it's Z cross Z is a fundamental group. And so in some sense, the neutral causal topology, the term topology refers to this fact, to this non-trivial topology in the null cone. The second thing that we need to define are null planes, so totally null planes. So a plane P, an element of R2, 2, is null, is totally null actually is probably the phrase we'll use, is totally null if, again, the metric restricted to that plane is 0 everywhere, is identically 0. Now, of course, this wouldn't exist in a Lorentz metric, but in signature 2, 2 with this split signature, in fact, the set of all totally null planes, so if you look at all totally null planes, this set, there's actually two disjoint unions of S1s. Each one of those represents a totally null plane. And this disjoint union, we often call these the alpha planes, and the second one there we would call the beta planes. Okay, so that's the second definition that we need. Again, it's all to do with nullity because of the indefinite signature in this metric. The nullity is an important aspect of this geometry that doesn't exist in the definite case. The third definition, again, it's to do with nullity, is the following. So if we take a hyperplane, so again, we're working all at each stage here in R2, 2. Let's a hyperplane, let's call it H in R2, 2, is null if it's normal, the normal vector. So let's call that normal vector n is null. So we say the hypersurface is null if its normal is null. So g of n is 0. Now, hyperplanes are quite interesting in the following senses. If you take H, then suppose it's the set of all vectors, all the vectors x, such that g of x comma n equals 0. Well, this is the hypersurface that are all the vectors that are orthogonal to n, but in fact n is an element of H. So this hypersurface, because of its nullity, actually contains its own normal. Okay, so suppose we start out with the null vector and we define H as above, and define H to be all the vectors orthogonal to it. So then we can construct a double null basis. So construct what's often referred to as a double null basis. So in terms of the metric, your original metric would have been 1, 1, minus 1, minus 1, with zeros everywhere else. And with the double null basis, well, we can take a null factor in the first term, so it's 0 on the diagonal, and 1 and 1, 0, 0, 0, 0, 0, and also down here. So it's as if we diagonal. We took this diagonal element, and each one of those we rotated them to make them into a double null basis here and a null basis here. So if we have that there, and if we take, for example, suppose that's your null vector n, and suppose we call this f0, and we call that e plus and e minus. And if we look at the space of vectors that are orthogonal to n, well, in fact, we get this diagonal down here. We get down here with this corner down here. And what we see is that the metric restricted to this hypersurface has signature 0, 1, minus 1. It's degenerate Lorentz. So null hypersurfaces, their metric are degenerate Lorentz. In fact, from that then we can look at the null cone on the hypersurface. So you can look at the null cone on this H. And when we do so, what we find is that it has the following eigenstructure. Following structure, I guess. So it has your normal vector, which lies in the hypersurface H. And then I guess if you call that E plus and that E minus, they're the other null vectors. And this is a totally null plane. So this is a totally null plane, all in this hypersurface. Both of these are. And in fact, one of them is alpha and the other is a beta plane. Okay, so we see that a null hypersurface in a neutral metric has this interesting structure. It's a pair of planes which intersect upon on the normal vector, which is null, and then it has a pair of null vectors in these two planes, so that every vector in these two planes have 0 length. So from that point, from there we can actually generalize all of this. We've done all of this in R22 or R4, so all of this, so first thing is that all of this holds at a point on any neutral four manifold. It's just linear algebra essentially. And the second thing is that nullity, these three different types of nullity that we've described, are conformally invariant. So if you change your initial metric by a conformal factor, conformally invariant, the null, these structures stay null with respect to the conformally related metric. Okay, so that's the first, or background, if you like, to the material. Our first theorem is the following. So again, it deals with R22. So there exists a map F which goes from R to 2, and it takes you to the 4-ball. And there's a metric on the 4-ball which I'll call G tilde. And there's a function which takes this 4-ball into the reals, and such that 4 conditions. So the first condition is that F is a conformal diffeomorphism onto the interior of the 4-ball. So in particular, when I say conformal, I mean that the metric G tilde is in fact this factor here times G. So this function is the conformal factor for this metric. Secondly, this conformal factor vanishes on the boundary. And the boundary of this 4-ball, of course, is just S3. Topologically, this is all simple. And in the third property that we have is that this S3, this boundary, is null. Final condition that we discover from this particular map that we write down in the paper is that the gradient of this conformal factor, if you evaluate it on S3, it's equal to 0 on the Hopf-Link in S3. And we'll talk a little bit more about that in a while. But it has some interesting properties. So we have G tilde, and it's on the 4-ball, so it's on the 4-ball with S3 boundary. It has the following properties. Well, first of all, it's conformally flat. Well, that's obvious because it's conformal to the flat metric by the first condition. It's scalar flat, and I guess we could hope maybe it's Einstein, but in fact it's not. It's actually not the right condition for indefinite metrics. It's actually non-Einstein. In fact, probably a little bit more detail, if you take the Ricci tensor, it's a symmetric 4x4, and if you diagonalize it, you find that, well, it has non-zero diagonals down here, and 0 elsewhere. And if you restrict it to the hop link, so on the hop link, we'll see why this is of interest in a minute. In the hop link, it actually, these terms are 0. So it's actually 0, 0, 0, and then it has just 0, 2. So it's got non-zero eigenspace down there and 0 everywhere else. Now, if you look at the Ricci tensor of this metric is related to the Ricci tensor of the original metric, which of course is flat, by the conformal factor, the second derivative of the conformal factor. In fact, this is really the Hessian is more or less this thing here. So this is the second derivative of omega written as a matrix. So now the proposal, which is summarized a little bit at the end of the paper, is the following: is to use the conformal factor as a, so we can use the conformal factor of this neutral conformal compactification as a Morse-Bot function, to get a handle decomposition of your manifold. In which case, what we just have here is a neutral two-handle. So we kind of think of this four-ball picture that we just have constructed as a neutral two-handle. Of course, if in the Morse-Bot theory, of course, the second derivative, the eigenvalues of the second derivatives gives you the index of the handle. In this case, you can see it has index 2 because it has 2 positive eigenvalues due to its relationship to this conformally related metric. And so this is why this is a two-handle, because of that rank 2 in the Ricci tensor of the conformal factor. Okay, so with that, in fact, what it suggests is that we can use these two handles to do what I'll call neutral Kirby calculus. And let me outline some of the ideas I have around this. So let's start out and take our original space R22 with its metric, and let's put a tilde on it just to mean it's conformal compactification. So I just mean B4 with this metric, this tilted metric. So that's the conformal compactification. In fact, I'll put a tilde over a few objects, so I'll mean the conformal compactification. And of course, the boundary of this four ball is S3. And so let's look at this S3. So here we're looking at an S3, and we have this hop link. Now on these hop links, you have, let me just draw in these hop links. Essentially, these are the infinite future and infinite past of the space-like and time-like geodesics in the interior. So I guess you could think of these as, say, that's the space-like ones, and this maybe it's the time-like ones. And what I want to do is I actually want to take 2 copies of this. So let's take a second copy here. So 2 4-balls with S3 boundary. And what I'm going to do is I'm going to look at identifying, say we take a torus, a solid torus around this curve, and we take a solid torus around this one. And what we want to do is we want to identify these 2 solid tori and smooth the corners, in fact. And in fact, we want to identify these solid tori with a twist of 2. Twist 2. So you twist it twice. So this process, when you attach this to this, I'm going to refer to as attaching a neutral. We want to push the metric across both, so we end up with the neutral metric on the final object that we have constructed. So attaching a neutral two-handle is the phrase maybe we'll use for this process. Now when you do that, in this case, with the twist of 2, you end up with, now my drawing is not quite as good as I would hope, but we'll do our best. So here we have the plus and the minus. That's not too bad. There, so there's your plus and there's your minus. And in fact, that's that has an attachment of 2, and that's your minus. Now, what I claim is, in the first instance, is that this is a disk bundle over S2 with Euler characteristic 2. It's in fact the conformal compactification of TS2. And in fact, if we look at the space of oriented geodesics of R3, that's a 4-manifold. This is TS2. And if you take that and you look at its conformal compactification, I claim that this metric with this conformal structure at infinity is just the space of geodesics of R3 conformally compactified with its canonical neutral indefinite metric. Okay, so in fact, this can be extended somewhat further as follows. So what we've just done there is we've taken R22, we take its conformal compactification, and then what we've done is we've done a neutral handle attachment. We've attached a 2 handle with twist 2, and what we've ended up with is the space of, excuse me, find the right color. There we go. Space of oriented geodesics of R3 conformally compactified. And I claim that what we can do now is we can actually continue and we can do a second surgery. And when we do so, there's actually 2 choices. Again, we're attaching a neutral 2 handle with twist 2 at each case. So we start out here with nothing. Here, the Kirby diagram would just be that without any decoration of the conformal infinity. And then here, if you do a second time, what you're going to end up with is something that looks like this, 2, 2. Well, it's well known that this is, of course, S2 cross S2 minus a 4-cell, 4-handle. And in fact, there's 2 different ways to do this. You'll get 2 different conformal infinities attached. And this is the oriented geodesics of S3, the conformal class of that metric. And here it's L of H3. So the claim is that what we can do is we can take, starting with flat space, we can attach a neutral 2 handle and we get the geodesic space of R3, or at least its conformal compactification, and then we have 2 choices, and depending on how we attach the handle exactly, how we geometrically attach, topologically they end up being the same, you'll end up with either L of S3 minus a 4 handle, or the conformal compactification of H3, depending upon which way you attach these 2 handles at this point, the handle here at this point. Okay, so you can see the idea then is that we have a way of carrying along this neutral structure, and that not only that this Kirby calculus with natural kind of restrictions on it gives you a nice sequence of constructions which passes through the neutral, the canonical neutral metrics on the spaces of oriented geodesics of manifolds, 3 manifolds of constant curvature.